Thank you for joining us on Synthesis Workshop. On today's Research Spotlight episode, I'm very happy to have with us Dr. Abdusalom Suleymanov. Abdusalom got his diploma in chemistry in 2016 from the Higher Chemical College of the Russian Academy of Sciences in Moscow. He subsequently joined the group with Professor K. Severin at EPFL in Lausanne, Switzerland, where he recently got his PhD studying novel triazenes and solid-state luminogens. Currently, he works in the same group as a postdoctoral researcher. And from there, I'll hand it over to you, Abdusalom. Thanks a lot for joining us today.
Hello, everyone. Thank you, Matt, for the kind introduction and for giving me the opportunity to share some of my research in this Research Spotlight episode. In this video, I would like to tell you about my PhD project on the synthesis of tetraarylethene luminogens by CH vinylation of arenes with triazenes. Many traditional organic fluorescent dyes, such as fluorescein, are highly fluorescent in solution, but they become non-fluorescent or weakly emissive in the aggregate or solid state. And it happens due to the formation of intermolecular pi-pi stacking interactions, which quench the fluorescence in the solid state. Aggregation cost quenching, or ACQ, greatly limits practical applications of classical organic fluorophores with pi-conjugated structures in the areas where the utilization of a material in the condensed state is important. A reversed effect was recently found for such a simple molecule as tetraphenylethylene. Tetraphenylethylene is non-fluorescent in solution, but it becomes highly fluorescent in the aggregate and solid state because of the restriction of intramolecular motions of phenyl rings. And this phenomenon has been termed as aggregation-induced emission, or AIE. Since the discovery of AIE, tetraphenylethylene and its derivatives have found many applications in the fields of material science, organic light-emitting diodes, chemical sensors, and bioimaging. Synthetic procedures which are utilized to build tetraarylethenes for AIE applications are mainly limited to these three methods. First is the Mach-Murray coupling, which has a drawback of the formation of homocoupling side products in the case of unsymmetrical tetraarylethenes. Second method is based on addition reaction of diphenylmethyl lithium to benzophenones and further dehydration. This is the most popular method in the AIE field, but due to the utilization of organolithium reagents, it is not compatible with many functional groups. The third method is compatible with functional groups and is based on Suzuki cross-coupling reaction of vinyl bromides and aryl boronic acids. In our work, we have developed a new method that is based on direct CH vinylation of aromatic compounds with vinyl cations. Vinyl cations hold a big potential to be used in organic synthesis as vinylation agents. However, the convenient generation of these highly reactive intermediates still remains challenging. The traditional way to form vinyl cations is based on the solvolysis of vinyl triflates or vinyl halides. This process is known to be slow, reversible, and it requires harsh reaction conditions, which restricts the applicability of these reagents in fine organic synthesis as convenient vinyl cation precursors. Very recently, the group of Nelson has overcome this problem. They found an interesting approach to replace triflate with a weakly coordinating anion under very mild conditions. This method allows generating vinyl cations that can react with alkanes and arenes. Although this method is very mild and useful, broad applications of this system in synthetic organic chemistry can be problematic due to the limited accessibility and stability of these reagents. Our approach is based on the generation of vinyl cations from vinyl diazonium cations, which can be formed from stable vinyl triazenes by the addition of acid. The generation of vinyl cations from triazenes was first introduced in 1967 by Johnson Miller, and although it was published more than 50 years ago, it did not find any synthetic applications, and the reason for this is the lack of convenient methods to prepare vinyl triazenes. So we first have developed a methodology for the synthesis of vinyl triazenes from vinyl Grignard reagents and these specially designed butyl azides containing a leaving group. This reaction allowed us to obtain different vinyl triazenes with pyrrolidine groups in moderate to good yields. Afterwards, we have shown that vinyl triazenes can indeed serve as vinyl cation precursors. We were able to substitute triazine group in the presence of acid with many different nucleophiles like thiol, amide, fluoride, alcohol, phosphine, and benzene in a very fast and clean manner. In the case of benzene, we have an aromatic electrophilic vinylation reaction. This reaction has particularly attracted our attention, and we wanted to apply it to a broader set of arenes and make something useful out of it. We were interested to convert arenes, which are abundant and commercially available starting materials, into tetraarylethene solid-state emitters, using this triphenyl vinyl triazene reagent. We started with the synthesis of this vinyl triazene. We applied our newly developed methodology with this azido-butyl iodide reagent. We isolated a product in a very good yield. The product had a correct mass spectrum, but the structure did not match with the NMR data. And when we performed the single crystal X-ray analysis of the compound, we found that the product we obtained is not vinyl triazene, it is this triazoline heterocycle. At first we were a bit disappointed with this unexpected result, but then we found some interesting features for this molecule. It is fluorescent in solution and also in solid state. And at that moment we knew that there are not so many classes of organic compounds which emit in solid state. Taking into account this fact and also the fact that this transformation and the triazoline product have never been reported before, we decided to investigate this reaction in detail. We found that it is important to have 3 aryl substituents on the vinyl Grignard reagent in order to obtain triazoline products. We made some aryl substituted derivatives. We can also modify the azide reagent. Taking a shorter azide, we can make a triazoline with a 5-membered ring. With aryl azide, we obtained the benzofused triazoline. All these compounds are fluorescent in solid state. This triazoline shows aggregation-induced emission. As you can see here, increasing the amount of water in THF solutions decreases the solubility and forms aggregates that are emissive. Another interesting property we found for these accidentally discovered molecules, they are redox active. They can be oxidized and reduced reversibly at relatively low potential. We were able to synthesize the oxidized radical cation salt. We found that this radical cation is very stable. It was fully characterized by X-ray, EPR, and elemental analysis. We've noticed that the radical cation is non-fluorescent in solution. It means that we can switch the fluorescence on and off using electrochemistry. This phenomenon is called in the literature electrofluorochromism, and only few examples of organic fluorophores exhibit this property. Under visible light, we have electrochromism. We can switch electrochemically the color of the molecule from colorless of the neutral compound to deep red of the oxidized compound. For the benzofused triazoline, we have a switch between pale yellow and green of the corresponding radical cation. We were glad to discover a new class of triazoline solid-state emitters with electrofluorochromic behavior, but we still wanted to perform this transformation. We couldn't obtain this triazene reagent with pyrrolidine group, and since it is not crucial what type of substituents we have here, we decided to make a different derivative of this vinyl triazene. So we found that the coupling of the Grignard reagent with phenyl azide gives the desired vinyl triazene in high yield, and the procedure can be easily upscaled to gram amounts. We tried the coupling of the vinyl triazene with benzene in the presence of triflic acid. We found that the only product of this reaction was the desired tetraphenylethylene, which was isolated in almost quantitative yield. Next, we investigated the scope of the coupling on substituted benzene derivatives. For some monosubstituted benzenes, we have the formation of para and ortho isomers. For disubstituted ones, the reaction is regioselective. The coupling works as well with functionalized arenes, like this one with the ester group. The reaction with heterocyclic arenes works with moderate to good yields. For furane, we obtained only alpha isomer. For thiophene, a mixture of alpha and beta isomers. For N-methylpyrrole, the reaction worked quantitatively. Interestingly, the vinylation works as well with unprotected pyrrole. We have also synthesized the first TPE derivative of ferrocene. Next, we synthesized tetraarylethenes with polyaromatic hydrocarbons like naphthalene and fluorine. These compounds have previously been described for their enhanced electroluminescence properties. Pyrene is a classical aggregation cost-quenching luminogen, and by functionalizing it with triphenyl vinyl cation, we can turn it in one step into the aggregation-induced emission luminogen. We made fluorescent and AIE active benzocrown ethers, which have the potential to be used in cation sensing. For dibenzocrown ether, we demonstrated that twofold coupling is possible, and we could also selectively functionalize this bioactive steroid molecule, and the product can be interesting for some biological AIE applications. After successful testing of the reaction on monomeric substrates, we became interested to apply this methodology to polymers containing aromatic groups. So we could directly functionalize polystyrene, a cheap and commercially available polymer, Perylene C, This polymer is used as a protective coating for microelectronic and medical devices. And polyvinyl carbazole, a commercially available conductive polymer with many applications in material science, can also be derived with triphenylethanyl group. As you can see on these pictures, the starting polymers are weakly fluorescent, and the vinylated products are highly fluorescent and AIE active. On this slide you can see again how in one single step we can alter the photophysical properties of almost non-emissive polystyrene into fluorescent one. The polystyrene we functionalized is cross-linked, and we wanted to look at its swelling behavior in different organic solvents. Here you can see that in such solvents like toluene and DCM, the polystyrene is swelling well and becomes non-fluorescent. But in the solvents like hexane, methanol, acetonitrile, the fluorescence is still on because the polymer has poor swelling properties in them. So we can use this fluorescent polystyrene as a simple sensor for solvent discrimination, which works on the principle of AIE. In non-swollen polymer we have the fluorescence on due to the restriction of intramolecular motions, and after swelling the tetraarylethene groups solubilize and the fluorescence turns off. Here I'd like to summarize my talk. In the beginning I briefly introduced to you our vinyl triazene chemistry. We can easily generate vinyl cations from them by the addition of acid. We applied this methodology for CH vinylation of arenes. Using the triphenyl vinyl triazene, we can convert a broad range of different aromatic compounds, including heterocycles, polyaromatic hydrocarbons, supramolecular receptors, bioactive compounds, and polymers, into AIE emitters in one step. And during the course of the study, we have accidentally discovered a new reaction and new triazoline solid-state emitters with interesting electrofluorochromic properties. With that, I'd like to thank my PhD supervisor, Professor Kai Severin, for his guidance and support. I thank my colleagues from the Severin Group, our collaborators who helped us with the analysis, the EPFL University, and the Swiss National Science Foundation for financial support. Finally, thank you, Matt, for the invitation to participate in this synthesis workshop episode. It is a wonderful experience to contribute to this platform. I hope you enjoyed my presentation, and thank you for your attention.
Thank you for tuning in for this Research Spotlight episode, and thank you to Abdusalom for a really great talk. If you enjoyed the episode, please support us by subscribing and telling your peers about this podcast. And feel free to send us any questions and comments you have. Follow us on Twitter to stay up to date, and see you all next time.